Yeah, good evening, class. Yeah. So let's wait till 6:05, and after that we'll start the class. Let the other guys join, and then we will commence the class at 6:05. Yeah. So welcome to second class of this TA Electronic Theory of Solids. And in today's class, I'll be discussing some few of the problems which will be based on the Drude model, then density of state. So these are the main primary topics which I will be covering with the help of the numericals to make the concept further clear. So this 2D model and the density state, these pictures have been already discussed in by Professor Aragya in the first week of the class. So I'll be just covering 8 or 10 questions on that. And if you have any doubt, any question, you can ask in between. Or if you have any other question apart from these questions, you can definitely ask those ones. I'll be happy to address your questions and concerns. So let me phrase the first question, which is like uh, the Fermi energy of sodium is given. Let's say the Fermi energy of sodium F is 3.2 eV, and its resistivity, the resistivity at room temperature is 4.7 into 10 power minus 8 ohm time meters, And then the question which is asked on base of these two parameters is, first, what is the Fermi velocity? The Fermi velocity. And the second question which is being asked is the average relaxation time. Yeah. So this is the question. Now let's address let call this is the part A and the part B. So this is the solution section now. So in part A, it asks about what is the Fermi velocity. So to compute the Fermi velocity, you take EF is equals to half mv square. Where m is the mass of the electron. If any effective mass is not given, we will take the mass of electron as 9.1 10 power minus 31 kg. So V will be square root of 2 EF by m. And now let's just substitute the parameter EF, which is 3.2 eV. We will convert the eV into the joule by multiplying it with this value with 1.6 in 10 power minus 90. And if we do so, what we get is under root 2 times 3.2 into 1.6 into 10 power minus 19 divided by mass is 9.1 into 10 power minus 31 kg. So this is kg, the top part will be joule. So what you get is, if you solve these values, you will get around V to be around 1.07 into 10 power 10 power 6 meter per second. So this is your Fermi velocity. Let me denote it as by Vf. So this is the typical speed in typical speeds of the electrons in the sodium metal, basically. Now, in the part B, the question asks for what is the average relaxation time. It is basically the tau, which is the relaxation, which is the scattering time between the two electrons. So let's say it's an average scattering time which will be there between the successive collisions of an electron. Right? So that we know that sigma is ne square tau by m. This comes from the Drude model. So if I take inverse of it, what I will get is rho is m by ne square tau, and tau, which is the relaxation time, which is asked in the question. If you just in just manipulate this equation 2, and this is let me call this one as equation 1. If you manipulate the equation 2, what you will get will be m by ne square rho. Right? So taking the n, which is the sodium electron density, let me also define it in the question also, so that it becomes clear, to be roughly 2.65 into 10 power 28 per meter cube. So let me define the problem only. Electron density is around 2.65 into 10 power 28 per meter cube. Yeah. So this is the sodium electron density. You substitute the value. So 9.1 into 10 power minus 31 kg by n is 2.65 into 10 power 28 per meter cube times 1.6 10 power minus 19 square times your resistivity, which is given in the problem as 4.7 10 power minus 8 ohm meter. If you solve this number, what you will get is tau to be roughly around 2.1 into 10 power minus 14 seconds. So this is roughly a time in which the successive collision happens in like the metals. So the time constant of this relaxation is roughly around 10 power minus 40 for typically for all the metals. So if I combine in summary, the Fermi velocity Vf is approximately 1.07 into 10 power 6 meter per second, and your relaxation time tau is roughly around 2.1 into 10 power minus 14 second. Yeah. So this is the solution for this kind of the problem. So this is how you approach. So to equate the Fermi velocity, basically, yeah, to equate the Fermi velocity, you equate it with the half mv square, and then estimate the Fermi velocity Vf, and that turns out to be 1.07, 10 power 6 meter per second. Now similarly for the second part, which asks for the average relaxation time. So it is that's basically the relaxation time is the time between the two successive collisions, basically the average time between two successive collisions in a metal. And this tau, we know that from the Drude model, sigma is n square tau by m. So if we take inverse of it, we'll get 1 by sigma is rho, which is resistivity, equals to m by n square tau. You just manipulate this equation, taking tau on this side, rho on this side. So now you have the form tau is equals to m by n square rho. You substitute the values of the electron mass, which is 9.1 power minus 31 kg, which is m. Carrier density is given. Electronic charge is, we know, 1.6 power minus 19 coulomb. And the value of the resistivity given in the question. If you substitute those values, what we get is the relaxation time, which is around the order of 10 power minus 14 seconds. Yeah. So roughly the scattering happens in the system on the scale of tens of femtosecond. And that's why the physics of these attosecond lasers, which are 10 power minus 18, gets important, because now you can just probe the electron dynamics, basically the scattering dynamics, all those things with like with the way higher resolution. So femtosecond laser, attosecond lasers, and they become very important at these time scales. Basically, if you want to see how the electrons are moving, how they are scattering, that's where this time scale gets important. So I think last year, no, yeah, last year, Nobel Prize was given in this field of uh, the laser, basically the attosecond laser development, which is 10 power minus 18 second. Yeah. So having said that, if I move on to, if you guys have any question, you can ask. Like if you have any doubt in any questions or solution, you can ask. I'll be happy to address that one. Okay. If no question is there, then I will just go on phrasing the another problem, which is like if you go pass on the 2D model and apply it to the thermal conductivity also, and you take ratio of thermal conductivity and electrical conductivity times the temperature, what you will get is like a quantity which is constant, which is Weizmann-Franz law constant, basically. And from there, uh, that's the universal law, basically. So the next question which I'll phrasing will be based on that. So let's say the relaxation time in aluminium metal is tau is roughly 2.5 into 10 power minus 14 second. So relaxation time in metals is around 10 power minus 14 second. Now using the Weidmann-French law, So what is the Weidmann-French law? It says that K by sigma T, K is the thermal conductivity, sigma electrical conductivity, T is the temperature, is equals to constant. And then constant is 2.44 into 10 power minus 8 Kelvin square. So now the question asks, like, what is the thermal conductivity? Conductivity at T is equals to 300 Kelvin, right? So it is asking for the thermal conductivity K. So we can, this equation is given, let's call this equation 1. So in the solution part, the K we can write as L times sigma T, but we are given quantity L, we are given quantity T. Now we'll have to estimate the quantity sigma in order to calculate the K, thermal conductivity. So this is thermal conductivity. K is thermal conductivity. Yeah. So we know that sigma is nothing but Ne square tau by m. M is the electron mass, E is the electronic charge, tau is given, and if we take, okay, in the question I should also define your carrier density. So roughly carrier density is 18.1 into 10 power 28 per meter cube. Yeah. So this is also given. So now substitute. Let me call this equation as 2. This equation is 3. So substituting equation 2, equation 3 in equation 2, what you will get is K is equals to Ln square tau by m times the temperature. So what it tells is, like, if you know the electrical conductivity of a metal at any temperature T, then you can tell, like, precisely what its thermal conductivity K will be, and that's kind of a universal law, right? If you basically you have any system in which you can measure the conductivity. Let's say you measure the resistance of a wire, right? And you know it's at room temperature. Let's say it's sitting at 300 Kelvin, and the wire you measure its diameter, you measure its length, diameter, and its resistance you measure with just a voltmeter and ammeter, and now you know the conductivity, electrical conductivity. But by knowing the temperature, roughly in the number density you can take to be in a material is always constant. So for, like, if in aluminum it's 18.1, knowing those things, those parameters, you can roughly tell what its thermal conductivity will be. The other way around is, like, for the metals, if it is a good conductor of electricity, it will be a good conductor of heat also, because K is directly proportional to sigma, which is electrical conductivity. So if a material is good conductor of electricity, it will be a good conductor of heat also. That's what this Weidmann-French law also tells, right? So this is about the concept. Now if I just take K is equals to N L, if I substitute the values, so 2.44 into 10 power minus 8, this is Weidmann-French law constant. Then carrier density is 18.1 into 10 power 28. E square is 1.6 into 10 power minus 19 square. Tau is 2.5 into 10 power minus 14 divided by mass is 9.1 10 power minus 31 kg, and total quantity multiplied by temperature, which is 300. So if you solve this one, it's just a numerical part. So you will get around 240 roughly meter inverse Kelvin inverse. So this will be your thermal conductivity. which you estimate using the Weidmann-French law. So just by knowing the electrical conductivity, temperature, carrier density, and the scattering time, you know what its thermal conductivity will be, which is very surprising because these two phenomena are very different. The way the electron conducts the heat and the way the electron conducts the uh, electricity, they are different. But still, this if you just correctly model the equation in most of the material metals, this law holds. So this is about the Weidmann-French law and the problem based on it. Like, it's like based on MCQ basically. Yeah. If anyone has question, they can ask in the comment section or by just speaking loud and turning on the mic. If there is no question, I will move on to the third problem basically, which is based on the density of states. Okay, it's a good question. How to estimate the value of the density? Right. I'll just first address this question. How we estimate? Okay. How to estimate the value of density? So the way you do is like in a material, density is roughly constant. Let's say when aluminum, density will be constant. So you take your material like this. Let's say this is a bar of your material. This is one of the experimental methods I'm telling you. Like how can you do it? And you apply a voltage here. So the current will flow in this one, right? If it's an aluminum bar. Right. So between these 2 points, this is Rxy. If you measure resistance like, okay, this is, let me just make these four contacts A, B, C, and D. If you measure resistance between R, A, B, it is called as longitudinal resistance because it is in the path of the current. So the current is moving in the x direction, and you also measuring the resistance along x direction. It's longitudinal resistance. But if you measure along RCB, let's say, it will be a transverse resistance. Because then you will be in the y, you are measuring in the y-axis, your current is flowing in the x-axis. So if you apply a magnetic field B, this is perpendicular basically to this your geometry of aluminium. So your RXY, RCB, which will be RXY, is will go as minus B by NE. So you know your resistance which you are measuring in RXY. So your number density you can calculate. Magnetic field, which whatever you applied, you know. Electron charge, you know. Rxy, you just substitute the value here, and then you can estimate the carrier density in a system. Like because if no magnetic field is applied, all the electrons will go along this direction only. Rxy will be 0. For B equal to 0, Rxy is 0. But if B is non-zero, since your electrons are moving like this, magnetic field is perpendicular, there will be a Lorentz force which is F equal to Q V cross P that will make the electron drift along this line along y direction, and then that develops the potential that gives you Rxy, and it is a this comes from the Drude model itself, that Rxy will be minus B by NA, and then you can estimate your carrier density. This is how it's generally done in case of the 2D materials and all the quantum Hall effects, these phenomena which are like topological things, there you estimate the carrier density using this method. Yeah. So is there any other question? If you guys have any question, you can write in the comment section and I'll just address it. So if not, then I'll move on to the next question, which will be question third. And this will be based on the density of states. So density of state just simply means that your number of available states per unit volume or per unit volume per unit energy. That's your density of state. So DOS is del N by del E, right? Where N is your number of states per unit volume and E is your energy. So this is your density of state, right? Now a for electrons in a metal, let me phrase a question. The density of state for electrons in a metal is GeDE is equals to 1.5 times 10 power 27 square root of E dE. Actually, density of state is GE, not, yeah, this is density of state. Okay. Then, if the electron density is also given, m is equals to 6 into 10 power 28 per meter cube. Calculate the Fermi energy. T is roughly equal to 0. So we know that the Fermi distribution function, that if your, right, this is your Fermi distribution function, probability of occupation. So if you go higher than this energy, basically, right, till this point the states are filled, and after that the density of state is 0 on this axis. Here this tells you the probability of occupation. Here it's 1, 0, and after that Fermi energy EF, your density of state is again 0, right? So this is for t equal to 0. For finite t, your Fermi distribution function goes as like this. Let me just draw the t equal to 0, and then in that only I'll modify. So this is EF, and if you are sitting at a finite temperature, let's say KBT, take it in another color, KBT, then a Fermi distribution function will be like this. Yeah, so it will be like this. So at finite temperature, your probability of occupation at Fermi energy will be half. This is 1, this is 0. And these are the states which are of the KBT order. These are also the states of the KBT order. So this is like for finite t, this is for t equal to 0. Since in the question the case is given for t equal to 0, so we will take the Fermi distribution function of this form. So this is the correct one for our case. If you have temperature dependent part, then you have to account for that also. Okay. So now the density of state for the electron in metal is given. The electron density is this. Calculate the Fermi energy. I see. So it's an easy problem where you just have to integrate it, and then you'll get your answer. Yeah. So your density GE is 1.5 into 10 power 27 square root of E. If you look at this form, density of state is nothing but GE. So this is what is given, right? So first you can do is integrate this equation. So this will be dN is equals to GE times dE, and if you integrate this one 0 to N, 0 to EF to Fermi energy, So this will be n 0 to EF, so 1.5 into 10 power 27. If you integrate square root of E, you will get e to the power 3 by 2 divided by 3 by 2, and then you put your limit of 0 to EF till the Fermi energy, and here 1.5 into 10 power 27 times EF to the power 3 by 2, and if it is 1.5, this is also, so n is 10 power 27 times EF to the power 3 by 2. You substitute the value of n, which is already given in your question, 6 into 10 power 28. EF to the power 3 by 2. So this will be 60 to EF to the power 3 by 2. So EF will be 60 to the power 2 by 3. And if you do so, you will get 60 to the power 2 by 3 is roughly around 4.4 eV. Okay, this is, let me just define, its dimension were not defined. This should be EV by EV by, this is density of state, right? So meter cube by EV. Yeah, meter minus 3 EV. It should have these dimensions. So cube EV inverse. Yeah. So this is how you calculate the Fermi energy. If your density of state is given, then the relation which goes is density of state is del N by del E, energy is equals to density of state. G is given, you integrate it to get the answer in the form of number density and the Fermi energy. And then if the number density is given, you can back calculate the Fermi energy EF, and that turns out to be 4.4 eV. Is there any question on this one? Okay, if there is no question, then I will move on to the next question, which is like deriving the relation between the Fermi surface wave vector k and the carrier density n. So this will be question 4. So for a two-dimensional free electron gas, two-dimensional means the electron's motion is confined in, let's say, x and y direction only. It's confined in the z direction. It can only move in the x and y direction. So that's kind of the two-dimensional electron gas. You can think it like the gallium arsenide two-dimensional electron gas, or the case of the graphene, in which the electrons, single layer graphene, in which the electrons are only confined to move along that particular sheet of the atoms, and that's known as the two-dimensional electron gas. So for a two-dimensional electron, free electron gas, the relation between electron density n and Fermi wave vector k is what? So if you have seen any band structure kind of thing, let's say for the for the two-dimensional electron gas, I'm drawing like this is the parabola kind of thing, where energy goes as k square, h bar square k square by 2m. Generally we know. So if this is the case, then these are like the available states, right? You have this available state, this available state. This is, I'm drawing in 1D because I can draw it only one, like in 2D basically. But if you see this Fermi surface wave vector will be like this. This area will be spanned like this. right? These circles, and Kf is this one. This is the wave vector Kf. Now, to do so, if you start filling this one, you will have to fill the carriers, right? One electron, two electron, three electron. Then only you, let's say you are at n electron, then you put n plus one, you move up in energy. Then you put n plus two, then you move further up in energy. That's how you move. So you change the carrier density, n, right? In n versus k space. And that's where this relation gets important, because experimentally, most of the time in transport, you don't measure energy. You measure your carrier density, and then you back calculate your Fermi wave vector using different techniques. Like there are experimental methods also through which you can measure, like Subnico-de-Haas oscillation, when de-Haas, when alpha effect, all those things are there. But the question primarily is, what is the relation between Kf and n? So let's say the number of the states, the total number of states will be in two-dimensional electron gas will be integral of area in K space, times area real space, right? And then 2 pi square. Right? So let's say your material in which you are doing so has area A. So since area will be constant, real space area, so you can take the n by A, right? And then you have area in K space by 2 pi square, right? So this will be the momentum basically. If I'm talking about the K space, then no need to take the h bar. If I talk in the term of the momentum, then I'll have to take care of the h bar in the bottom. So this will be 2 pi square. So either I write area in momentum space by 2 pi h bar square, or I write area in K space by 2 pi square. Both are accurate. Yeah. So if you have any region in the K space, you can model it like this, right? A ring and a circular ring, another circular ring, right? And this region, so you can fragment it like it has radius k, so its circumference will be 2 pi k, right? And then this width of this ring is, okay, let me just move the color. So the width of this ring particularly, which you are seeing here, is dk. Then you write the area element here as n by a is equals to integral 0 to kf till Fermi surface area in 2 pi k dk by 2 pi square. And if you do so, that you will get will be number density n. N by a is number density, is k square. So this 2 pi goes here in the downside, k square by 2, and 0 to kf. So n will be kf square by 4 pi. So this will be the relation between the Fermi wave vector kf and the carrier density n. So this is the general, this is for if there is no degeneracy. If the two-dimensional electron gas is non-degenerate, I mean there is no degeneracy at one energy, one kind of state is there, right? But it can have degeneracy also. So let me just assign here. Let the system have degeneracy. Degeneracy of 2 or G, let's say, right? Generally, there is a degeneracy of 2, either spin up or spin down. So the degeneracy will come here in the front part, multiplication. So this will be G here, G here, and G here. So the general relation is this one. So this is the relation between number density and wave vector kf for degeneracy of g. In the question, degeneracy was not given, so you take g equals to 1. If it is spin degenerate, you take degeneracy of 2. If it is a graphene system, then you will be having 2 spin and 2 valley, so you take g is equals to 4. So let me write for non-degenerate. G is equals to 1, so you get n is equals to kf square by 4 pi. For spin degenerate, like normal material, normal metals, what you will get, G is equals to 2, so your n will be kf square by 2 pi. And for graphene, which is a two-dimensional material, spin and valley degenerate, so there's a spin degeneracy of 2 and valley degeneracy of 2. So you get n is equals to kf square by pi. So these are the three different cases. The question asks for the first case, but in general the question can be asked for g equals to 2 or n times degenerate or graphene. So this should be your answer. Is there any question on the case of the degeneracy, on the way how you calculate the density of state, and the wave vector, the radial area which we took in the case of breaking the area in the term of the disk of the radii decay, all the things. Like if you have any question or doubt, you can ask in the comment section. Okay, looks like no one has any question to ask. If that's the case, then I will move on to the next problem, which is, let me think, which problem should I pick? Okay, I'm sorry, just 1 second. I'll take a call. Yeah, I'm sorry. There was an urgent call which I had to pick. Okay. So let me phrase another problem then, which will be like, that you have a like wire of copper of length 500 meter, a copper wire of length 500 meter and is connected to a 12-volt battery. And the drift velocity for an electron to travel through the wire is closest to. Yeah. Is there anyone who wants to address like how to approach this problem? Okay, drift velocity also let me give is roughly 10 power minus 10 power minus 4, 10 power 6 meter per second. Let me just give you the drift velocity also 10 power 6. Generally, by the way, let me check the drift velocity for electron in copper. I will give you the exact value only. So let me just Google it. Drift velocity of electron in copper. Yeah, it's 10 power minus 4 meter per second. So the drift velocity is 10 power minus 4 meter per second. How long will it take? How long will it take for the electron to pass the copper wire? Okay, so the problem is like you have a copper wire, and think it like in your home you have your lights, all those things are connected, and the power is coming through copper wires or maybe aluminum wire, I don't know. So this length is 500 meter, right? Your electron from your power grid or transformer, like in your nearest transformer, is coming to a wire. This is your point A, and then it comes to this point B, which is the end of your wire, right? How long will it take for the electron to go from point A to point B? So we know the basic relation, right? Speed is equals to distance upon time, right? So drift velocity is given, so you can estimate the time also. The t distance is around 500 meter, and this 12-volt battery doesn't matter, like it doesn't count because any small potential will be able to move your electrons at the same speed. And if drift velocity is 10 power minus 4, then in that case the time taken will be, this will be in the seconds. So 500 times 10 power 4 seconds. 500 into 10 power 4 by 3600 or 60 minutes. And yeah, so if I convert into the minutes, it will be 60, and if I convert into the hours, it will be these many hours it will take. So if I just roughly calculate this value, this turns out to be around 1388 hours, and if I divide it by 24, I'll get around T to be 57.87 days. What does it mean? Can anyone tell me like why these values are like 58 days, roughly 2 months it will take? But your home, in your home, the wires lengths are around 500 meter, right? But you turn on the switch, immediately the bulb lights up. It doesn't light up like 2 months later. So what does this the drift velocity mean then? Is there anyone who would like to address this problem? Because this is a genuine problem, right? You say that okay, electron moves with a drift velocity vd, right? So to go from A to point B, that electron will take around 2 months. But when you turn on the light, immediately your screen lights up, your mobile starts getting charging. All those things happen instantaneously, right? Why it is so? Is there anyone? Okay. No, length is, even if you reduce the length by, let's say, I reduce the length by 10 order of magnitude, right? Instead of 500 meter, let's take it's 550 meter, which is very genuine length in your home, right? The length of your wires in your home, 50 meter, right? Then also the time will go down by a order of magnitude. A order of magnitude will still be around 5 days, right? If it is 57 days, I divide it by 10, then also it's 5 days. But you turn on the bulb, it instantaneously lights up, right? It is not like that you turn on the bulb and it will light up 5 days later. It lights up immediately. Why it is so? Okay, you get AC current at home, so the electron don't have to travel the entire length. No, even if in the DC case also, you have a 12-volt battery, for example, in this case. Even if you have an AC current, that's the same scenario. And your AC is not of very high frequencies. It is up to 20 hertz. It's in the DC limit only. It's not very high frequency AC. 50 hertz is nothing. I mean, 50 hertz, 20 volt, 50 hertz is DC limit. Right? The reason electron takes so long here is because they are experiencing collisions. I think Rushikesh is answering this one. Okay, right? This is right because this drift velocity is small indeed, because the electrons are colliding with each other, and that leads to, because this reduction in your drift velocity. But that still don't answer, right? Because generally we in our home we have copper wires, and we turn on the bulb, it lights up instantaneously. Okay, let me then answer this one. So think it like you have this one. This why the bulb lights up instantaneously, even though from going from point A to point B, the electron will take around 2 months. The reason is it's filled with electrons, right? The full thing. Your material is filled with like 10 power 28 electrons per meter cube. That high density. You apply a voltage of 12 volt. As soon as you do, what actually happens is you are applying an electric field, right? An electric field is an electromagnetic wave that travels with the speed of light, right? So the signal in your system travels, the electromagnetic field will travel speed of light. So it is not like this electron will go and light your bulb. Even the electron which is sitting at very edge in the wire, that will also starts moving. Everything will starts moving instantaneously. And it's not this electron at point A will go to the point B to light up the bulb. Yeah. So this is the reason, because electromagnetic waves moves at speed of light. That is 3 into 10 power 8, at least in the vacuum, is the speed, right? So that's how the signal transmits like very fast, uh, and your bulb lights up instantaneously. Yeah. So if this is clear, then maybe we can take one more question. Let me see, like what should I take so that it covers the basic concepts of the class at least. Yeah. So density of state, if I just take this question, del n by del E, we can take, yeah, maybe we can take this density of state question. This will also be good. Yeah. So calculating the density of states for different systems, right? So the question which I phrase is the density of states for a one-dimensional free electron gas varies with energy as. Okay, so your density of state is there. Option A is GE, which is your density of state proportional to square root of E. Option B, GE goes as energy. C, your density of state GE goes as 1 by square root of E. And D, your GE is constant. So what will be the answer? Anyone who wants to answer this question? Is there anyone like who knows what the answer, how the density of state varies with energy? Okay, so I think it's Dipanita. She says that option A is right. Okay, is there anyone else? Okay, now Rushikesh is saying that option C is correct. So is there anyone else like who wants to bet on option B, D, A, C? Okay, if since the group one has pointed as option A to be the correct answer, another to point C, so we'll have to derive it, right? So to clear the doubt. Now we know the density state I defined GE as del N by del E, right? Number of states per unit energy, per unit volume. So let's first calculate the total number of states in 1D. So in total number of states in 1D will be your area in K space. So basically in 1D it will be length. So length in K space times length of real area of real space divided by 2 pi, right? So n by length of real space, let's take L. Then length in the K space will be K by 2 pi, right? So your K is your N by L is your number density N. So your N is K by 2 pi. This is in your 1D 1D system. Okay. Now we have the relation between N and K, but we want the relation between N and E and take the derivative with respect to it to get the density of state. So for free electron, we know energy is what? H bar square K square by 2m, right? So if your K will be what? E and basically square root of 2me by H bar square. So this is equation 3, this is equation 2, and this is your equation 1. So substituting 3 in 1, 3 in 2, substituting equation 3 in 2, will give you n is equals to under root 2 me by h bar square and then 2 pi. So let me just take this one as constant, right? So because otherwise I will have to carry it every time. A times square root of e, where a is 1 by 2 pi square root of 2m by h bar square. That is a constant. So now n and a are dependent on this relation. N is equals to a square root of e. But I will have to take del n by del e. That will be a square root of e, derivative will be half and e to the power minus half. That I can write a by 2 and square root of e. Right? This is a density of state G. So Ge will go as 1 over square root of e. This is for 1D system. For similarly, if you do it for similarly, if you do it for 2D system, you will get Ge is equals to constant for 2D. This exercise you can do for 2D and 2D system, and for 3D you can do the same exercise and you will get that n the density state will go as square root of e for 3D. This is for 3D systems. Yeah. So if I draw it on a graph, this is your density state, if I axis, and this is your energy, then the graph for 1D will be like this, square root of e. This color means 1D. Then for 2D it will be constant. This color means 2D. And for, I'll take some other color, maybe this one, yeah. And this is how it will be for 3D. This is for 3D. That's how your density state will go for 1D, 2D, and 3D system. So the correct response is C. So GE goes as inverse of square root of energy. Is there any doubt or question on this one? The way we calculated the density state and the energy expression? Okay, so if there is no question, then maybe we'll end this class, right? And I'll see you in the next class. And if there is any question, you can ask in the comment section or drop me a mail at mohitchat@iisc.ac.in. I'll be happy to address your concerns. And along with this, again, I'm saying, like, if you have any mm, intensive kind of interest or someone who you know that they are more inclined towards doing the physics part of it, those who enjoy doing the uh, experimental research, please write up to me with your CVs. Maybe we can see if there is an intensive position in the department or at the institute, and can give you some plenty of opportunities to work for at least a month or two in the experimental lab to get like an idea like how the things goes in the research area, so that you can. Okay, and the book basically, the books which I follow is Ashcroft Marmin and the Kittel. I find them like very basically accurate in terms of saying the words, and they are the fundamentals in the case. They are the fundamental books in particularly the electron theory of solids or the condensed matter, whatever you say. and that's so. Yeah, Ascroft Marmin and the Kittel will I will prefer. It will mostly clear up your doubts, and it has example problems also, which you can see. And yeah, okay. So one is Ascroft Marmin, another is Charles Kittel. So this is, and the another is Kittel, Charles Kittel. So I prefer Ascroft Marmin the more because I was first introduced to Ascroft Marmin, then the Charles Kittel. So that's why it's my more kind of favorite. I'm more inclined to this book. But I heard that the people also enjoy Charles Kittel. So this is something which you also can follow. And if you guys want to get a copy of it, I will add a copy of it in the class notes, which I'll share maybe today or tomorrow. Copy of these books. So I'll add a soft copy. Of course, mm, that's not the correct way of distributing the copies because there are copyrights, all those things. But yeah, I'll add the copy of the Escort Mamin and the Charles Kittle so that you can follow it. Yeah. So if there are no question or doubt, then thank you class for being here and being patient for at least an hour. Uh, I think Rushikesh is typing something. Let's take his question and after that maybe end the class. I think it's Mar. Okay, it's Marmin. I wrote it's Marman. Come on. Now I can see it. I have written it. So this is Marmin. Yeah. Have a nice day. Thank you. Bye bye.